Okay, so in the last class, we had a look at some of the general properties of linear equations. In this particular class, we will look at the flow in a corner. In particular, the sweeping flow in a corner. And this solution was given by Moffatt. So let us see whether we can reduce the set of Gurney equations. So the Gurney equations are minus grad T plus nabla square u equals 0 combined with the equation of continuity. Now, is there a way to convert this equation into something simpler? Essentially, we want to reduce it to a equation with a single variable. So, how can we do that? So, given that the velocity field is divergence free, we may write the velocity field as a curl of some vector. Everyone knows this. So, the velocity field can be written as a curl of some vector. And let us consider a two-dimensional field where the flow is sort of confined onto a plane. So, the flow is confined to a plane. We want to construct a velocity field which is the curl of a vector and it is confined to a plane. Any vector A can be also written as psi grad phi. So, what is curl of psi grad phi? It will be equal to grad psi cross grad phi. If you want to confine the flow onto this particular plane, the velocity field we know exists in this particular plane. So, grad psi must exist as a vector in this plane. So, suppose these are the vectors of grad psi. These are the vectors of grad psi. The gradient of psi is a vector. So, iso psi lines will be something like this, and iso psi lines gradient is the sort of normal to all the lines and is a vector which points in that particular direction. We all know the physical meaning of grad psi. What about grad phi? So, if grad psi is in this direction, grad phi has to be in this direction. Grad phi has to be in this direction in order that the curl of grad psi, which is this, the curl of this vector and this vector be confined to this particular plane. Okay. Therefore, if grad phi has to be in this direction, what should be phi? So, phi obviously has to be simply equal to z. So, if you have planes of iso z like this is one z, this is another z, this is another z, okay. So, this is z1 equal to constant, this is z2 equals constant, this is z3 equals constant. So, grad z, essentially grad phi, is pointing in this direction. Pardon me. Yeah. So, grad phi is pointing in this direction. Therefore, the choice of the velocity vector is equal to the curl of psi times grad of z, which is nothing but curl of psi times Ez. So, the velocity vector is given by this. Essentially, you may recall this from the stream function definition. Now, what about the Gurney equation? So, the Gurney equation is minus grad p plus nabla square u vector is equal to 0. So, it should be clear that this is a dimensionless form. Otherwise, there will be a viscosity term over it. We can eliminate pressure. how can we eliminate pressure? So the pressure appears as a gradient. So we can take a curl of this equation. So curl of this entire equation. Essentially, curl of grad P will be 0 because the curl of a gradient is 0 plus nabla square times curl of u equals 0. So what can we do with this term? So we recall that u is curl of psi Ez. So before proceeding to that, let us see what the divergence of the velocity is. It is identically 0. So let us see. So it is the Laplacian of vorticity, which is equal to 0. Okay. But if the velocity field is confined to this particular plane, if the velocity field is always confined in this plane, then the vorticity vector must necessarily be pointing in this plane. Therefore, omega is actually always omega pointing in Ez direction. I hope this is clear because the velocity fields are in this direction in the plane, and vorticity can only exist orthogonal to the plane. So it will be always 0. And therefore the simple equation is the Laplacian of omega is 0. Let us see what the definition of omega is in terms of psi. In terms of psi, omega is defined as nabla cross u, and this is nabla cross psi. And essentially this is minus of Laplacian of psi Ez. We have made use of the vector identity. Okay. There is a vector identity which helps us to write this particular term, and I leave it as a home task for you, just to show that this entire thing boils down to this. So omega Ez is equal to minus Laplacian of psi Ez, because again omega is only pointing in the Ez direction. So because this vector equation is in this form, we can write omega is minus Laplacian of psi. So essentially we reduce the governing equation. Let me write it again. Into the following form. So if we substitute omega from this equation into this equation, we then have a consolidated equation only for psi. And then we need to solve only for psi. Once psi is known, we can find out the velocity field by substitution. So these equations, they are sort of the vorticity-stream function formula. Okay. So in 2 dimensions, we have obtained reduction of the equations in the vorticity-stream function formula. What will happen if instead of a planar 2-dimensional flow, we have a 3D 2-dimensional flow? So by 3D 2-dimensional flow, I mean a 3D flow which depends only on 2 independent variables. So consider a flow past a sphere. If there is a uniform velocity field over here, then the flow past this sphere will be axisymmetric. If the flow is axisymmetric, then this angle is theta. So the angle in this particular plane that angle will be phi. So let me read the in a Cartesian system so that you can understand. So this angle is theta, this is the radial coordinate, and the projection that it makes, the angle of the projection is phi. So naturally, the entire problem, if it is axisymmetric, it will not depend on phi, it will only depend on r and theta. Therefore, a three-dimensional problem can also be represented in the vorticity-streamfunction formula. But what will be the appropriate choice of the vector? We have already seen that the velocity is the curl of psi grad phi. So what should be phi in the case of an axisymmetric field? What is the choice of phi? So we know that if the flow is independent of phi, like in the case of 2D, we knew that the flow must be held onto a surface which is iso z. So the flow is sort of constrained onto a surface which is iso z. Similarly for this, the flow has to be held onto a surface which is iso phi. Let me draw quickly the surface. So given this phi, this entire surface which has a constant phi is sort of the surface onto which the entire flow will be confined. Okay, so phi will simply become phi. So in that case, u vector will be grad of chi e phi. So the curl of chi e phi rather. So you can now make use of the expressions for curl of a vector in spherical coordinate system, and we will do this in the future class. So we can do the curl and find out the governing equation for the vorticity in terms of the string. But for today's class, we will focus on Cartesian 2D flows. Rather not Cartesian but planar 2D flows. We will focus on planar. So the governing equation, let me reiterate, is this and subjected to the appropriate boundary condition. Now we can write these two equations in two rather convenient coordinate systems. By no means they are a complete set of coordinate systems, but we can have various coordinate systems, but a Cartesian and a cylindrical polar are very convenient to solve various kinds of problems. Let us write down the equation. Rather, before writing down the equation, let us see what the problem of Moffatt was. Suppose we have a plate which is fixed like this, and we have a long plate. This is a long plate, it extends to infinity. So this is like a scraper. So this is like a scraper, and you are sort of pulling this plate. You are pulling the plate with a velocity capital U. So this problem is reminiscent of various coating industry applications. So what is the nature of the flow in this particular zone? So the fluid resides in this zone and there is nothing over here. So in this zone, what is the nature of the flow? So it is convenient for us to fix a coordinate system at this particular point. Okay, so this will be R and this will be theta. So obviously the lower plate is theta equal to 0. And let us denote the upper plate by theta equals alpha. So the governing equations in a more fundamental form in terms of velocity are minus grad p plus nabla square u equals 0 along with nabla dot u equals 0. We know that these two equations are transformed into these two equations. So, but still we keep it like this for now. But what are the boundary conditions? What are the boundary conditions? So the boundary conditions are u r equals capital U at theta equal to 0, and for all r u theta equals 0 at theta equals 0. That is to say, so this particular component will be u theta and this particular component will be u r for the case of theta equals 0. For the case of theta equals alpha, the plate is not moving, so the fluid will have to honor both the no penetration and no slip. So ur will be equal to 0 at theta equals alpha and u theta will be equal to 0 at theta equals 0. So this is the definition of the problem. This entire thing is the definition of the problem. So we can convert the governing equation into the form that we desire. What happened? Oh, that should be theta equals alpha. So now we must cast the boundary conditions in terms of psi and omega. So first of all, let us see how we can write down the velocity. So the velocity in terms of psi is nabla cross psi Ez. We must now write down the curl of a vector in the cylindrical polar coordinate system. We can look up any appendix of any mathematics book. I am writing down the direct solution over here, and it is very easy to obtain. Just do it. So UR, from this operation, we will obtain UR as del psi by del theta, and U theta will be equal to minus del psi by del R. Okay. From this particular operation, see, because the operand, the curl is operating on a vector which is pointing only in the Ez direction. So the curl should not have any uz component. It must necessarily have only ur and uz component. So the curl of this, when you do it, will yield ur as 1 by r del psi del theta and u theta as minus del psi del theta. So the boundary conditions are as follows. So ur is equal to 1 by r del psi del theta, and that is equal to u for all r at theta equals 0. Now this particular boundary condition itself sort of indicates that in order for this thing to be valid for all r, psi must necessarily be of the form r multiplied by some function of theta. It is only when psi is some r multiplied by function of theta, then r will cancel from the numerator and denominator, and we will have only a function of theta equal to u. So remember this, psi will only be of this particular form. It cannot be of any other particular form. So the boundary condition, first boundary condition is 1 by r del psi del theta equals to u. So if you substitute this particular form, it will be 1 by r d d theta of r into f of theta equals u at theta equals 0. Essentially saying df d theta equal to capital U at theta equals 0. for all r. Then what is the second boundary condition? U theta equals 0 at theta equal to 0. Essentially implying minus del psi del r is equals 0. So minus del psi del r equals 0, implying f theta, rather minus f theta equals 0 at theta equals 0. Similarly, the other two boundary conditions are ur equals 0 at theta equal to alpha, which implies df d theta equal to 0 at theta equals alpha, and u theta equals 0 at theta equal alpha, which implies f is equal to 0 at theta equal to alpha. So the four boundary conditions are del f del theta equal to u at theta equal to 0, f theta equal to 0 at theta equals 0, df d theta equals to 0 at theta equal to alpha, and f equals 0 at theta equals alpha. So these are the four boundary conditions. And the first boundary condition has also prompted us the form that should be chosen for psi in order to have a consistent equation for the first boundary condition. Any other form of psi, if you include any other power of r, will not yield the appropriate boundary condition, and hence this particular choice of boundary condition is the only consistent form. Okay, so now let's solve this problem. So in cylindrical polar coordinate system, we have this. So 1 by r del r of r del psi del r plus 1 by r square del 2 psi del theta 2 equals minus omega. This is the equation. And similarly, Laplacian of omega is equal to 0, meaning 1 by r del r of r del psi del r plus 1 by r square, no, this is the omega. 1 by r square del omega del theta, del 2 omega del theta 2 is equal to 0. So let us first evaluate this equation. We know that psi is equal to r times f of theta. So what is this? So let us see what del psi del r is. Del psi del r will be simply equal to f. Then what r times del psi del r will be? So r del psi del r is equal to r times f. Then del r of r del psi del r will be f. Then 1 by r del psi del r of r del psi del r will be f by r. So this left hand side term is simply f by r. What about this term? This term will be 1 by r square del 2 psi del theta 2. So del 2 f times r divided by del theta 2. So this is, so r comes out because this is a derivative in theta. So this simply becomes 1 by r d2f d theta 2. If we combine this term and this term in this particular equation, we obtain f by r plus d2f d theta 2 times 1 by r is equal to minus omega. Essentially implying omega is minus 1 by r d2f d theta 2 plus f. Now we can substitute this particular form of omega in the equation for omega, essentially which is the Laplacian of omega equals 0. So Laplacian of omega equals 0, we can substitute this omega over here. So what is del omega del r. So del omega del r will be 1 by r square d2 f d theta 2 plus f. So what is r del omega del r? It is 1 by r d2 f d theta 2 plus f. So what is del r of this term? It is minus 1 by r square d2 f d theta 2 plus f. Then what is 1 by r times this? Minus 1 by r cubed d2 f d theta 2 plus f. So this term is the first term. What about the second term? The second term is 1 upon r square del 2 omega del theta 2. So essentially it is 1 by r square times minus 1 by r, because this 1 by r comes outside the derivative of theta, times the second derivative of this entire term. So d4f d theta 4 plus d2f d theta 2. So if we combine the first and second term, we have minus 1 by r cubed d2f d theta 2 plus f, and the second term, which is minus 1 by r cubed d4f d theta 4 plus d2f d theta 2. This is entirely equal to 0. So 1 by r cube can get cancelled, because this equation is actually not valid at r equal to 0. So we can cancel r from all sides. So essentially we have d4f d theta 2 plus twice d2f d theta 2 plus f equals 0, subjected to the boundary condition. So let us write the boundary condition solely in terms of f. We have already done that. df d theta is equal to u at theta equal to 0 and so on. So I will just write it down over here for convenience. So df d theta at theta equals 0 is equal to u. df d theta at theta equals alpha equals 0. F at theta equals 0 equals 0. And f at theta equals alpha equals 0. So this particular equation is subjected to these boundary conditions. So what is the solution for this? So we can assume that f is of the form theta to the power m, e to the power theta. We can assume that the solution is e to the power m theta, right? So what do we have? M to the power 4 plus 2m square plus 1 is equal to 0. Essentially m square plus 1 whole square is equal to 0. So the roots are repeated roots. So it is plus minus I and repeated roots. So the 4 roots of this are e raised to I theta, e raised to minus I theta, and theta e raised to I theta, theta e raised to minus I theta. Alternately, we could have written this in terms of sine and cos. So the 4 roots are sine theta, cos theta, theta sine theta, and theta cos theta. So this is from elementary differential equations. You should be knowing this. And thus the solution can be written in the form f is equal to a sine theta plus b cos theta plus c theta sine theta plus d theta cos theta. So the first boundary condition is df d theta. So let us, before writing down the boundary condition, let us quickly write down what the expression for df d theta is. So a cos theta minus b theta minus b sin theta plus c sin theta E theta cos theta plus B cos theta minus B theta sin theta. Now we can write down the four boundary conditions. So the first boundary condition gives df d theta equals capital U. So capital U at theta equals 0. So A, so this will be 0, this will be 0, this will be 0 plus B. So A plus B is equal to U. Now what about this boundary condition? That will say 0 is equal to A cos alpha minus B sin alpha plus C sin alpha plus C alpha cos alpha plus B cos alpha minus B alpha sin alpha. And then the two other boundary conditions are f is 0 at theta and alpha both. So 0 equals, so setting theta equal to 0 in this equation, we have B only. So B is equal to 0. And then theta equals to alpha in this equation. So 0 equals A sin alpha plus B sin alpha plus C alpha sin alpha plus B alpha cos alpha. So these four equations are to be solved in order to find A, B, C, D. But you already know that B is equal to 0. So if B equal to 0, the equation reduces. So this equation reduces to 0 equals A cos alpha plus C sin alpha plus C alpha cos alpha plus B cos alpha minus B alpha sin alpha. And this equation becomes 0 equals A sin alpha plus C alpha sin alpha plus B alpha cos alpha. Okay. Along with A plus B equals 0. So 0 equals A plus. So let us eliminate what? We can eliminate A from this. Anyway, I leave it as a simple home task to you. It's just plain simple algebra. It's just a matter of solving these equations in order to find A, B, not B, A, C and D. Everything else is known. So I will write down directly the solution. I've done this before. We will not waste our precious online time solving this set of equations. So the eventual psi will be R multiplied by F, and it comes out to be R multiplied by minus capital U by sin square alpha minus alpha square sin alpha square sin theta plus sin alpha cos alpha minus alpha times theta sin theta minus sin square alpha theta cos. So this is the basic prefactor. This is the sin theta term, this is the theta sin theta term, and this is the theta cos theta term. So this is the expression for psi. Well, that's all well and good, but what do I do with this? So once you have the expression for psi, we can find out the expression for ur as 1 by r del psi by del theta, and you can find out the expression for u theta as minus del psi by del r. With the help of this, you can visualize the flow field. Now, after this, let us see. So this entire thing is very, very well behaved. At r equal to 0 also it appears to be very well behaved. But there is a catch. At r equal to 0, the length scale in the locality of the slot. So we are working in this region, we are saying that everything is small, the creeping flow is valid, blah blah blah. But in this region, the velocity is changing from u to 0 over a very small distance. So over this distance, it is changing in this particular radius. As you decrease the radius, as you go towards r equal to 0, the velocity is sort of adjusting from the plate velocity u to a 0 velocity over a very small distance. So the shear is sort of delta u by delta n. That shear magnitude increases tremendously. The expression for the shear stress tau r theta, I am writing it down, but you can look up any appendix of any fluid mechanics book to find out the expression for tau r theta in the cylindrical coordinate system. So tau r theta, I am writing down direct solution, is minus 2u by sine square alpha minus alpha square multiplied by 1 by r sine alpha cos alpha minus alpha. So this is when you substitute theta equals 0. So at theta equal to 0, essentially this plate, this is the expression for the shear stress. And the shear stress sort of becomes singular at r equal to 0. At r equal to 0, as r tending to 0, the shear stress magnitude is very, very high. And that blowing up nature of the shear stress implies that this particular approximation of the boundary condition may not be valid very close to the edge of the coordinate. But anyway, for today, we are happy by having the solution for the flow of Moffatt. In a separate video, I will quickly show how to plot that solution in MATLAB. But for you guys, you should be able to go to the video and actually solve for these. Don't be lazy. I mean, I personally use some kind of symbolic toolbox because I feel too lazy nowadays, but you can do it by hand. You can eliminate A, C and D each one by one and find out the expression in terms of alpha, sin alpha, cos alpha. In the final solution for psi you can construct, and if you are so enterprising, you can go on to MATLAB, plot how the stream function looks. You can also plot how the streamline looks. You can also plot a Fourier plot, so the vector plot of the velocity. So these three things you can do in your leisure, and you can envision various kinds of flow geometry. I will give one such problem in the homework. You can have various kinds of flow geometry in this kind of problem. You can have a dip coating kind of problem also. So a dip coating problem. You have a free surface of fluid and you have a plate which is immersed in the fluid, okay, and you are sort of pulling the plate. So instead of having a solid surface bounding the slot, you have a free surface. So this is sort of the problem of Moffatt, where the solid surface, the solid bounding surface is now replaced by a free surface. You can neglect all capillary effects over here. You can neglect it because capillary effect will try to cause the fluid to rise like this. So you can neglect those effects and try to find out the solution for dip coating. So dip coating, you take a batch of paint, you just dip your tool or you can dip your plate into this and drag it out. It's a very rudimentary way of coating things. So such kinds of problems are very important for industrial applications. And we have studied one such problem, which is the Moffatt solution. And we will, in a separate video, I will just upload it on YouTube. It will be the solution to visualize the solution of the Moffatt solution. With this, we end today's lecture, and I will see you next time.